on microbiomes, just very briefly. Those will give local ecological dynamics. I also want to give a very brief introduction to metacommunity theory, which will indicate how these things connect together. So there's going to be local dynamics, which will take the form of an ODE, of a dynamical system, and it will be connected through some network. Our modeling framework has 3 ingredients. It has the network. It has some dynamics of exchange, which is going to be the part that we generalize from sort of the ordinary theory that was already there, and it's going to have some local dynamics. What our paper does, I say our paper, it's really my former student, Michael Johnson, who graduated a month ago, has 3 different regimes depending on how fast the local dynamics are relative to how frequent interactions are between different hosts. Okay, and so those are 3 things that we work with, one by one in the paper, and there are theorems corresponding to each of the 3. And the main thing I want to give today, since I am also the only thing standing between you and a party, is that I want to give a flavor of the 3 different things just to get some intuition into what the important parameters are. And if you want details, that is what the paper is for. This paper has been on archive for 5 days, so it is fresh off the presses. Okay, so again, microbiomes plus metacommunity theory. So a microbiome, and this is going to be, again, one of our local things, is a connection of microorganisms. They're living together in some habitat. In our context, we're thinking of the habitat as a living host, but you can think of other contexts as well. They will substantially impact where they live, whether it's an environmental patch or a living host. And they'll also play a critical role in the functioning and health of it. Additionally, the host interactions, I phrased it as social interactions, but it's really any interactions between the different environments will also significantly impact the composition of the microbiome itself. So the relative abundances of different species that are in there. And so then we're going to model it in the context of a local ecological dynamics, which can take perhaps a traditional form like a Lotka-Volterra model, or it can take some other form. Okay, so this is a generalized, let's see if this is, okay, so this is just one example, a generalized Lotka-Volterra model. So you have, say, M species that are coexisting. And typically, I mean, people consider models both large and small ones. Each species will have an intrinsic birth and death rate, which is then combined into some parameter. So if it was left alone, what would happen? And then there are interactions, and this is done in a mass action form, pairwise interactions in this specific example, where the sign of alpha is going to be indicating whether one type of species is beneficial or harmful to another. If it's a positive sign, you get a positive interaction, so it's beneficial. If it's a negative sign, which is what you'd be used to in the traditional Lotka-Volterra, it is harmful. You can also consider other types. You can consider, this is known as a niche model. It's a type of consumer resource model where you now have competition for the same resource. So I'm not going to explain all the terms, but hopefully that gives enough intuition. So one of these patches, one of these hosts can have something like this, or it can also have some toy. I'll end up showing you numerics just with a toy, but it can have various types of dynamics, right? So that's what's going on locally in one spot. In metacommunity theory, you have a set of interacting things, right? So each local patch has some kind of dynamics, and they're linked through some network. And there's going to be dispersal of these species, and so you're going to be exchanging parts of the microbiome between these species. And so what metacommunity ecology will do, and there's a large set of people who work on this, both from a biological point of view and from a mathematical point of view. There's going to be local factors, which will be things like predation and competition and environmental conditions, or anything you want to put in an ecological model. And there will also be regional factors, which are how these things interact with each other. So you can have dispersal of individuals, you can have immigration, you can have emigration. And this is an attempt to explain patterns that are observed in species distributions across these multiple patches and scales. One way that they're often studied, and I'll show an example of an equation of what one of these things looks like later on, is known as a mass effects paradigm. So here I just have the quote if you want to Google it. This has continuous dispersal of microbes, and if you don't put in spatial effects elsewhere, we'll give you a couple set of ODs. If you put in spatial effects, they'll give you PDs. The thing that we do and that we spend time working on in this particular paper is, instead of having a continuous dispersal, is that we want discrete interactions. Okay, so that's the change that we make compared to what was there before. Okay, so Again, there's going to be some network, make it as complicated as you want. There's going to be some exchange dynamics, which we're taking in a discrete form for our purposes, and there's going to be some local dynamics you can put in your favorite ecological model there. So the network might look like this. Each host, so I'm actually using H for vertices, which is a little bit odd if you're doing graphs, but H because it stands for hosts. So you might have this, and they might be connected in some way. We are making our connections undirected, so this is an assumption that we make, so we have a symmetry between them. That wouldn't necessarily be true in general, but we are doing this. Associated with any one of these edges is going to be a parameter, lambda sub ij, which is saying how often, how frequently is there an interaction between host I and host j. Okay, so this can be heterogeneous if you want across different pairs. However, we are going to care, and one of the key model parameters that we're going to care about in terms of how we set things up for the theoretical results is going to be the total. So just summing over all of them, and we're going to want to bound that at some point to say, oh, our interactions are sufficiently slow, so the fastest one has some bound. Okay, so this parameter is going to show up again. So when we have exchange dynamics, so we have some abundances, and we have multiple abundances, so you might have 2 or 3 species or whatever it is, and you have a relative number of each one within each host. And if they interact at some time, so I've labeled it as T sub I, but anyway, interacting at some time, they will instantaneously exchange a proportion of their microbiomes. Okay, so they will be picked to interact, and there'll be some exchange, and we make a simplifying assumption that this parameter is the same for all pairs. That would not be true in general. Okay, so that's an additional simplification that we make in the context of what we do. So that's also going to be one of the ones that would be good to generalize in terms of reality and things of that sort. And so immediately after the interaction, you have this exchange. So you have 1 minus gamma of what you had before, and you have gamma of whoever you exchange with. Then you need the times to somehow choose the times at which these interactions occur, and that's going to satisfy some probability distribution. And so for simplicity, and this is just to make it convenient for us, we picked an exponential distribution, and then we're going to also want to know the relative frequency. So if I take my frequency of interaction, lambda ij, I know this is towards the bottom of the slide, and if you divide it by the total, this is saying how often am I picking hosts I and j versus picking some other pair. Okay? And again, the exponential is not because of any realism, it's because it's convenient and simplistic for us. Okay, so then you have local dynamics of the hosts. I gave a couple of examples that people study. When I show a numerical plot, I'm going to actually show it from a very toy example that is not ecological at all, but it's just a polynomial, but it's convenient because then we know exactly where all the attractors are, and that's something that's useful for us. But there's a function g. It has to satisfy certain things that I have not told you, but you can use whatever you want, whatever standard one you want. And again, I'm going to show numerics just with a toy. In this particular toy, there are 4 stable equilibria of the local dynamics, and the basins of attraction are colored as such. The x's are where the equilibria actually are, and the 4 different basins of attraction are there. Okay, this is of the local dynamics, and we're assuming the same local dynamics for each host. Okay, so we have 3 different regimes depending on the relative sizes of parameters, like lambda total, which is the total interaction frequency, and gamma, which is how much of the microbiomes get exchanged in each interaction. So what we call the low frequency approximation, so all the lambda j are small. What that actually means for us is that lambda total is small, and in the theorem statement is that lambda total would go to 0 to get the precise one. And so what happens there is that the frequencies of interaction between all hosts are guaranteed to be small, so you go and in the limit you approach your local attractor before there's a switch. And then you approach your local attractor again before there's a switch. Okay, so this is the idea that the local dynamics are going to apply, and then there's a switch. And this is the reason why you're getting things along these lines. This is first host, this is the second host. So this one only showing 2 hosts there. Okay, Okay, so hopefully that gives the right flavor. So I have the English and the math version. The math version includes some stuff that I did not define for you, and I'm not going to define for you. This is what papers are for. But again, I hope to convey the intuition. So the local dynamics is much faster than the exchange dynamics. Okay, this is the regime in which we're in. And so each microbiome abundance vector, so this is just a set of the different relative amounts, becomes close to the attractor before the next exchange. And then if you actually take the limit going to 0, if you take lambda total going to 0, then it'll become asymptotically close. And then you can actually define a sort of operator that will end up being accurate in this limit. I have not defined the operator for you, but we took some inspiration from quantum mechanics in terms of what we were thinking about. And we briefly, but probably intelligently, decided against using Brockett notation because, of course, the ecologists would love that. We will see what happens, but anyway. But the idea is that you can have so this basin and probability tensor is going to give the probabilities of being in each basin of attraction. And so it's saying for each of these hosts, I have probabilities of which of those 4 things, well, 4 for the dynamics I showed you, I'm in. Okay, so the idea is describing the relative probabilities of each attractor for your local dynamics. There are 2 high-frequency approximations. So in this case, instead of, from a theoretical point of view, instead of taking this lambda total to 0, we are taking the lambda total to infinity, right? So we're taking the frequency of interaction very large. If we take the interaction strength, which is the relative proportion of the microbiome that gets exchanged in one interaction, and let that go to 0 and allow the relative interaction frequency parameters to be fixed. So any pair ij is always having the same relative amount, and then you have a fixed product. So this starts looking a little bit statistical mechanical. You have your total interaction frequency going to infinity, but you have the strength going to 0 as long as this product stays fixed. If you do that, you actually recover a mass effects model, right? So that you recover a notion of continuous dispersal instead of having discrete dispersal. And this is an example of what a mass effects model looks like. You have your local dynamics, and now you're actually writing this as an ordinary differential equation instead of having your stochastically chosen times of when interactions occur. So you have this sort of effective dynamics recovering the types of models people study. And then there's a statement of a theorem. I don't know if I'm going to not start going through it because I don't think I can explain it properly in this context anyway. The one thing I will say is that this 4.2 is exactly a mass effects model. It's just that it's this product lambda ij times gamma that's playing the role of this dispersal rate, which I wrote abstractly over here. Okay, then we have the third one. Interactions are again very frequent, and they have what we phrase as constant strength. So we're still having in the theoretical statement lambda total going to infinity. Okay, so we still have that, and we're still fixing the relative amounts that we're choosing each pair. But now we're also fixing gamma instead of fixing the product of gamma and lambda total. Okay, so it's a different thing that we're fixing. And what happens here is that instead of reducing the mass effects model, what we're doing is that very rapidly each abundance vector converges rapidly to the mean of all the vectors. So you get a form of synchronization. I'm using the word synchronization loosely. I know there's different ways of defining terms like that. But we're getting a form of synchronization in which everything ends up following the mean. And again, there's a theorem statement that goes through it. And then you can see this is the statement of the mean dynamics that each thing is following. Again, various things that I didn't bother defining. I'm going through this much faster than I thought. Well, anyway, more time for partying. Okay, and then for the conclusions, I was trying to not go through things too much. Okay, so, well, I'm going to have another slide after this, but just to remind you, if you want to see this, the paper is on archive. If you look at it and you have comments on it, we're happy to hear. It will be a while before we hear from referees. Okay, so we developed a framework to model microbiome dynamics of living hosts. We're incorporating local dynamics. Metacommunity theory does that within an environment. And we have exchanges, but the difference is that instead of just having continuous dispersal, we purposely want to have discrete exchanges in how we do this. And we had to consider different interaction frequencies. We also made a bunch of simplifications. So the fact that we're taking gamma is this relative proportion of microbiomes being exchanged being the same for each pair of hosts, that's not realistic. right? That's completely for simplicity. The fact that we drew things from an exponential distribution, I suspect is not realistic. I don't have the biological knowledge to know that. But again, we made the choice because it was convenient as far as where we drew things from. So there's a bunch of situations where it can be where things can be generalized, and we think it's doable to generalize it. My student has gone now and started a math finance job, so it will not be him who's generalizing it. So at the moment, this is where we are, but we think that people can also build on what we have. We will again see what the referees tell us. The thing that I liked about kind of this way of doing it is that we have distinct parameters to separate network structure and dynamics and local dynamics and what exchanges. And one of the things that I'm very interested in, I was trained in applied dynamical systems, but I've spent a bunch of my career working on a lot of things with networks. I like the idea of saying, how does network structure affect the dynamics and which things are controlled by which things? And the way that we kind of formulated this problem and separated things, I'm very happy about how that has been done. And so we made a bunch of simplifications in the process is what we did it, but I thought that we separated in a good part, and I wanted to convey in this talk kind of how we did that. And then we have 3 different regimes with one theorem corresponding to each. Okay, thank you very much for your attention.
Questions for Mason?
Silence is always great. Yes.
Yeah, how does your model differ from other model with like disease and the social opinion?
Right. Right. So it sort of depends, right? Because I can put in the local dynamics. I could put in fact, the dynamics that I show the numerics from is sort of this fake dynamics, right? Like I could put in disease dynamics within that. So you could try to look at that for disease dynamics if you wanted to. As far as how it differs from existing ones, they don't tend to be thinking of it in terms of having these discrete interactions, but you can try using for that. I haven't tried yet. I think it's reasonable to try, at least in principle. You're welcome.
Could that also have a station in like social science?
You could. So I should, in terms of the background about why we were doing microbiomes and thinking that way, I mean, I had a grant with ecologists to work on microbiomes, and so this was pitched as a microbiome project in terms of what I wanted a student to work on, and so that's why we had that as a motivating example, and why we were thinking about models that came from that and what we were doing. But I do hope that the sort of idea and how we split things up can also be used for others. I mean, I think it can be, but someone has to spend the time to actually do it in practice.
Listen, thank you.
Oh, there's someone, I thought, is that a question?
I'll talk to
No, okay.
Oh, no. I just heard that the microbiome, not microbiome, the stomach microbiome varies a lot from person to person.
It does.
I understand.
Absolutely.
And so the numbers, these species are going to be different from
Absolutely. Yeah, absolutely. So we made them the same because we want the vectors to have the same dimensions.
Size.
Yeah, no, that's absolutely right.
But my understanding is what's affecting, I have good friends who have just, problems with their gut, and it's the changing the species is kind of one of the things, right? How do you control what are the more beneficial species?
Right. So we don't address that. I think that the issue with different numbers is a bit of a cosmetic issue with respect to that, because we could just set some of them being 0. I don't think that's a big problem in terms of what's beneficial or what's not. We don't distinguish, right? We just have species 1 through S. Right, we don't make that distinction. I mean, this is definitely. I mean, the way we've done this is definitely a dynamical systems problem.
Okay.
As far as microbiome versus microbiome, everyone pronounces it differently. This you can my ecology collaborators on the grant and I. We actually had this. There was this discussion, and Chris Klossmeyer, who's one of the people who's on this, insisted that we should call it microbiomes. I'm like, okay, fine. You're the ecologist. You know better than me. But we did actually have that actual discussion.
Okay. Thank you very much, Mason. So now.